There's one other thing that I wanted to talk about before moving on to specifics. And it's something which is maybe strictly speaking not essential, but it's one of those things that if you actually wrap your head around it, it makes this so much easier. One thing that I really kind of learned from my experience in the world of engineering is that sometimes a picture, people say a picture says 1,000 words. In the world of engineering and physics and things like that, sometimes a picture saves you from 1,000 equations. So if you can think about these things in terms of pictures and diagrams, you can end up saving yourself a lot of mathematical headache. So how do you go about thinking about energy visually in terms of pictures and stuff like that? In the problem that I solved in the previous video, it gave you a potential energy function that was like 500 joule times meter over z, and it asked you like if you release the object from rest, will it move in the positive or negative z direction? Now I had kind of a long-winded argument with words and numbers to try to figure out the answer to that question. It's much easier to figure out the answer to a question like that visually. In other words, graph this, okay? What does this look like? Let me see if I can do it a little bit neater than that. Okay, let's graph this guy and see what it looks like. Okay. So this graph is Z is here, and this axis is the potential energy. So the form of this potential energy is 1 over Z. So I'm sure you know what 1 over x looks like from your math courses. It's something like this, where it blows up to infinity at z equals 0, and then it gradually goes to 0 as z increases. Okay, now, if you look at that curve, you can actually figure out immediately what an object is going to do if you release it from rest in this potential energy. And here's how. Just as I talked about in the previous video, kinetic energy cannot be negative, and if kinetic energy goes to 0, the object will stop. So let's say that you release an object here at this z coordinate. Okay, so say this is your initial z coordinate for the problem. In the last problem, it was z equals 10 as the initial z coordinate, but whatever it is. Will that object move to the left or will it move to the right? Because kinetic energy can't be negative, the object is going to move in the direction that decreases its potential energy. Let me just write this down because this is important. Objects tend to move in the direction that decreases their potential energy. If you make that statement a little bit more precise, I have to appeal to your knowledge of Newtonian physics for a second here, which I don't usually like to do in the world of energy, but let me at least say it. The object experiences a force which points downhill on the potential energy graph. So if you're thinking about this in terms of like forces, the force on the object is going to pull it down towards lower potential energies. So like there's a force on this object in the positive z direction, and I can tell that from the graph because that's downhill. Another way you can think about this is the behavior of the object on this PE graph, on this potential energy graph, will be the same as an object which is rolling on a surface that is shaped like the potential energy graph. So in other words, if you ask the question like what would happen to this object in this potential energy, the answer is actually the same as what would happen to a ball if you released it on a ramp shaped like this. And the answer is obviously that it would roll down the ramp towards larger and larger values of z. It would roll this way. And the reality is the same, that the object would move in the positive z direction. And it's just that simple, trying to wrap your head around what the object would actually do. Let's do a little bit of a more complicated example. Let me flip over to my lecture note PDF so that I don't have to try to draw a complicated thing by hand. Okay. So like, for instance, here's a very complicated fun. We're not going to attempt to actually quantitatively study any potential energies that are this complicated in the course, but in real life, of course, potential energies are extremely complicated, especially in the world of like biology and the human body and things like this. So you often encounter in reality these wavy potential energy functions that are hard to talk about mathematically. So let's say, for instance, that you release an object here. Oops, got to get my drawing tool out. Let's say that you release an object there, and you want to know what's going to happen to this object if you release it from rest at that potential energy. So first observation is, as I was talking about a second ago, we know that it's going to roll downhill towards lower potential energy because it's headed for this minimum. But then what's going to happen after it gets to the minimum? And the answer can be found in, if you think about the analogy of a ball rolling on this surface, what's going to happen is the object will overshoot the minimum. It'll start to climb the hill on the other side, but then as it was heading down towards the minimum, it was speeding up. But now as it starts to head up on the other side, it's slowing down. And how high is it going to get? How high is it going to roll on the uphill portion? And the answer can be found in conservation of energy. The object's potential energy, and if it's released from rest, its total energy is this level here. Let me maybe use the straight line tool instead of trying to draw this myself. The object's energy is this amount of joules, that horizontal line. You notice that this line I just drew, that's associated with a value on the y-axis there of how much potential energy it has. And if it's released from rest, then the potential energy initial equals the total energy. And since the kinetic energy can't be negative, if it's released with this amount of energy, it can't get up past that level because it can never have more potential energy than it started with, because it can never have more total energy than it started with. So that means it will get to exactly the same height as where it started, and then it will stop because its kinetic energy is now 0 again. It'll stop, and then it will turn around and roll back down to the bottom again, and then it'll roll back up the other side, and it will get to that level again, and it will stop and turn around, and it will roll back and forth around that minimum in the potential energy curve. That's exactly the same thing you see with, if you release a ball on a ramp, it will roll back and forth around the minimum. The same thing tends to happen with objects due to their potential energy. This is not something we're going to overly dwell on too much in the course, but if you can read off a potential energy graph this way, you'll have a lot easier time wrapping your head around what's going on with a lot of the potential energies that we will soon be studying.